We're going to begin our unit on reactions in aqueous solutions, starting with observable properties of acids and bases. So it says when an acid or base is dissolved in water, we'll start with taste. What do acids taste like? They taste sour. So anything that has a sour taste, oranges, lemons, any other food or drink that tastes sour is because of an acid. Bases, on the other hand, taste bitter. So hopefully you know some examples of substances that taste bitter. So just know that they taste different. What if you were to touch a solution of an acid or touch a solution of a base? So now I'm talking about a situation where you have a dilute solution of acid or base. So not talking about concentrated acid where it's going to burn your skin. But what would a solution, if an acid got on your fingers or a base got on your fingers, what would it feel like? Of course, before the burning sensation that could occur, solutions of acids feel the same as water. However, bases feel slippery. So if you've ever done a titration where you're using a base in the burette and your burette is leaking and you touch that liquid, you're going to feel it slippery. If it's slippery, that is definitely your base. All right, reactions with metals, and you notice it says non-oxidizing acids such as hydrochloric acid or hydrobromic acid, not something like nitric acid. And don't worry about what a non-oxidizing acid is. So acids, do they react with metals? Bases, do they react with metals? Yes, we've seen this. Metals do react with acids, and when an acid reacts with a metal, one of the products is hydrogen gas. If you were to add a metal to a base, no reaction would occur. How about electrical conductivity? We've talked at great length about this. In order for a solution to conduct electricity, it must have ions. So let's say you have a solution of an acid or a solution of a base. Will those solutions conduct electricity? And if so, to what extent? The answer is yes, they both will. And those solutions will be fair to excellent conductors of electricity. So some solutions of acids are excellent conductors of electricity, and some are so-so conductors of electricity. Depends on the amount of ions in those solutions. Next up, we have indicators. So indicators, may want to make a note. These are chemicals that are different colors in an acid or a base. Not always, but they're different colors technically at different pHs. We haven't talked about pH yet, but that's really what it is. A chemical that's one color at one pH and a different color at a different pH. There's two that you need to know of. Litmus. We will use this in at least one of our labs, probably two of them. What color is litmus in an acid? What color is litmus in a base? There's actually two types of litmus paper. You have red litmus paper and blue litmus paper. So if you were to test red litmus paper in an acid, that litmus paper would stay red. If you tested blue litmus paper in an acid, the blue litmus paper would turn red. Kind of the opposite for bases. Red litmus paper in a base will turn blue. Blue litmus paper in a base will stay blue. We're not going to use litmus too much. We'll use it again in a couple of our labs, or use litmus paper. We will use in our other titrations phenolphthalein, very commonly used indicator in acid-base titrations. What color is phenolphthalein in an acid? What color is phenolphthalein in a base? So phenolphthalein is a colorless solution. In the presence of an acid, phenolphthalein remains colorless. In a base, in the presence of a base, phenolphthalein turns pink or magenta, or sometimes people call it red. There's a picture in your textbook on page 382. You may want to take a look there. On the far right is a picture of the titration at the equivalence point, where the indicator is phenolphthalein has now turned pink in the presence of that base. There are several definitions of acids and bases, 3 to be exact. First one, I think the spelling is wrong in your notes. It's called the Arrhenius definition. An Arrhenius acid is a substance that, when dissolved in water, forms hydronium ions, or H3O plus ions. Hydronium, by the way, is the same thing as an H plus ion. So if you take an H plus ion, add it to a water, H2O, you make H3O plus. So either one of those, a substance that produces H plus ions in solution, or a substance that produces H3O plus ions in solution. Now, just to change it up a little bit, because I'm looking ahead, technically an acid is a substance that increases the concentration of H plus ions in solution, or increases the concentration of H3O plus. Bases, Arrhenius base is a substance that when dissolved in water increases the concentration of hydroxide ions. So basically, no pun intended, an acid is anything that produces H plus ions, a base is anything that produces OH minus ions. Let's take a look at some examples. I'm going to write an ionization equation for the acid and a dissociation equation for the base. So hydrochloric acid is a strong acid. It will dissociate. Technically, the term is ionize completely, and you make these ions. So because that substance produces hydrogen ions in solution, by definition, it is an Arrhenius acid. When you put sodium hydroxide in water, it will dissociate into these ions. Because this substance produces hydroxide ions in solution, it is considered an Arrhenius base. Another definition is known as the Bronsted-Lowry definition, sometimes just called Bronsted definition. Bronsted-Lowry. A Bronsted-Lowry acid is a substance that can donate a proton to another substance, a proton being a hydrogen ion. Now think about that. A hydrogen atom consists of a proton, one proton and one electron. Take off the electron to make the H plus ion. What are you left with? It's just a proton. So we're going to follow the hydrogen ions. We'll see an example in just a bit. A base is any substance that can accept a proton from another substance. Namely, it's going to accept that proton from an acid. So we have a transfer of a proton, and it goes from the acid to the base. All right, next up we have conjugate acid-base pairs. A pair of compounds or ions that differ by the presence of just one H plus unit is called a conjugate acid-base pair. Take a look on page 352. And we'll do some examples like this in just a bit. So just taking a look at, say, letter A. Let's write the equation for the ionization of nitric acid in water. If you did look down at the solution, nitric acid doesn't really react with water, but it's shown reacting with water. And you produce nitrate and hydronium ions. The HNO3 and the NO3 minus are conjugate pairs. They differ by just one H plus. Likewise, the H2O and the H3O plus are also another conjugate pair. So two substances that differ by one H plus. By the way, the acid, if you're looking at a conjugate acid-base pair, the acid will have one more H plus than the base. Likewise, the base will have one less H plus than the acid. All right, let's take a look at another example. It says write the balance equation for the reaction between hydrofluoric acid and ammonia and identify the conjugate acid-base pairs. Let's go ahead and do that. Typically, when you have a weak acid, weak base, we're going to write it with an equilibrium arrow. I'm not too concerned with the type of arrow that goes here. But when you're identifying conjugate acid-base pairs, we usually do use this double arrow. All right, so what's going to happen here? Well, hydrofluoric acid is an acid, both according to the Arrhenius definition and the Bronsted-Lowry definition. Ammonia is a base, and so the HF is going to donate a proton to the NH3. So when the HF donates a proton, what does it become? Well, it's going to lose an H plus, so it turns into, don't forget about the charge. It's not just losing hydrogen, it's losing a +1 charge, so you get F minus. If NH3 gains an H plus, what does that turn into? Again, don't forget about the charge. So typically what we'll do is we'll link up the conjugate acid-base pairs as shown here. And we want to label each substance as an acid or a base. Let's go ahead and do that. Now, if HF is an acid, then what is F minus? Has to be a base. Well, if NH3 is a base, what is NH4 plus? It's got to be an acid. All right, so how about this? HF is a stronger acid than NH4 plus. So notice in this solution, let's say we have a solution. We have all four of these substances present. HF is a stronger acid than NH4 plus. This information would need to be provided to you. I'm just telling you now, HF is stronger acid than NH4 plus. Now be careful, I'm not talking about the ability to ionize, the degree at which it ionizes. I'm looking at it from a different viewpoint here. So what this means is that HF is better at donating a proton than NH4 plus. So both HF and NH4 plus want to donate a proton. HF can do this better. Therefore, which side of the equilibrium is favored? What are you going to have more of at equilibrium? Reactants or products? Go ahead and pause the video and give your answer. Since HF is a stronger acid than NH4 plus, the products will be favored, meaning there will be more products at equilibrium than reactants. All right, go ahead and try this one on your own. Write the balance equation for the reaction between hypochlorous acid and ammonia. Do the same thing we did on the last one, and then answer that second question there as well. Go ahead and pause the video and handle that. So there's our conjugate acid-base pairs, labeled each as an acid or a base. NH3 is a weaker base than ClO minus, meaning given the choice, which one is more likely to gain an H plus, that would be the ClO minus is more likely to gain an H plus. And because of that, then the reactant side is favored this time. Next up, we have amphiprotic or amphoterics. Let me give you the spelling on that. Amphiprotic, amphoteric substances. These are substances that can act as either an acid or a base, meaning they can either donate a proton or accept a proton. Let's take a look at the case of water, and let's show water reacting. It doesn't really react, but reacting with HCl and reacting with NH3. So go ahead and label conjugate acid-base pairs. So with hydrochloric acid, with HCl, water acts as a base where it is accepting a proton. Let's show this same type of thing with ammonia and water. So this time the water is donating a proton to the NH3, so the water is acting as an acid. So depending on what you put with it, water can donate a proton or accept a proton. Go ahead and try this one on your own. We have the hydrogen phosphate ion, HPO4 -2. Write an equation showing it reacting with HCl. Write an equation showing it reacting with NH3. Identify the conjugate acid-base pairs. Pause the video. Alrighty, there's the equation showing how it reacts with an acid and how it reacts with a base. Thus, we see that it is amphoteric, can go either way. We've also talked quite a bit about acid-base strength. Just to remind you, a strong acid or strong base is a substance that ionizes or dissociates, either one of those, completely in water. On the other hand, weak acids, weak bases, are substances that only partially or moderately dissociate or ionize in water. As a result, these substances establish dynamic equilibrium with its ionized and unionized forms. Let's take a look at a demonstration of the conductivity of two solutions. I have 1 molar hydrochloric acid and 1 molar acetic acid. So let's see if there's a difference in their ability to conduct electricity. So kind of hard to tell, but we see that the hydrochloric acid is a better conductor of electricity. That tells us that solution has more ions. Why is that the case? It's because all of the HCl molecules ionize. The acetic acid solution, even though it's the same concentration, 1 molar, it does not conduct electricity as well as the 1 molar HCl. Why? Watch what I do with this equation. So we got that equilibrium arrow, two-way arrow, implying that not all of the acetic acid molecules ionize. Some of them stay in solution unionized. And as a result, you get less ions in solution, and so that solution does not conduct electricity as well. Let's go ahead and list out again the strong acids. There are 7 of them you need to know. 3 of them are binary acids, and 4 of them are ternary acids. So we have in order hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. Also need to know the strong bases. So a couple different examples of strong bases. Letter A, the group 1 hydroxide, so lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and francium hydroxide. All of those are strong bases. They all dissociate completely. And then some of the group 2 hydroxides are strong bases. Let's list those. Just those 3. So be careful with those. And then any other acid or base that we will encounter may be considered to be weak, unless we're told otherwise. So there are more strong acids than what is listed there. Next lesson, we'll talk about how to determine the relative strengths of both binary and ternary acids. And we'll be able to see some more examples of strong acids. But for now, we'll just focus on those. Anything else, we'll just assume that it is weak. Again, unless we are given information that tells us otherwise. All right, that concludes this lesson. Thanks for watching.